Good evening, everyone, and welcome to New Vistas in Astronomy, a lecture series presented by the Fred Lawrence Whipple Observatory, which is part of the Center for Astrophysics, Harvard and Smithsonian. I'm Nadia Whitehead, your host and a public affairs officer here at the CFA. We're pleased to present tonight's lecture, The Great Dimming of Betelgeuse, in a virtual format, streaming to both our Facebook and YouTube channels. We'll have time for questions at the end of today's lecture, but if you have a question during the lecture, simply type it into the comments on Facebook and YouTube, and we'll get to as many questions as possible at the end of the talk. If you're interested in receiving our e-newsletter and information about future lectures and events, please make sure to sign up for our mailing list by visiting the link that's appearing on the screen now, and it's also appearing in the comments section. Now, I'm pleased to present tonight's amazing guest speaker, Dr. Andrea Dupree, who will be presenting on the mysterious dimming of the star Betelgeuse. Andrea Dupree is a senior astrophysicist at the Center for Astrophysics, where she directs the Solar, Stellar, and Planetary Sciences Division. She is a past president of the American Astronomical Society and led and served on many committees for the National Academy of Sciences, NASA, the American Association for the Advancement of Science, and others to determine the future course of astronomical research in the United States and other countries. Andrea holds a bachelor's degree in liberal arts from Wellesley College and a doctoral degree in astrophysics from Harvard University. Andrea's interest in the star Betelgeuse began in the mid-1980s with measurements from satellites that documented the 420-day pulsation period of the star. Later, in 1995, Andrea led the team that captured the first image of a star other than our sun. The historic image of Betelgeuse in ultraviolet light was taken with the Hubble Space Telescope and revealed the star's brightly varying surface. Today, Andrea still studies Betelgeuse, most recently its great dimming in 2019. Now, please join me in welcoming Andrea Dupree. Andrea, thank you so much for joining us tonight. I'm going to let you pull up your presentation and take it away.
Okay, thank you very much, Nadia. I'm delighted to share the exciting things that have been happening with our friend Betelgeuse. So let me continue by hopefully bringing this all up, and we'll see if it comes, and it did, and that's wonderful. So what I'd like to do is tell you what Betelgeuse did, how the world reacted, what we think went on. We're still not 100% sure. Maybe we're 95% of the way there, but there are exciting things about this star. Now, I assume that most of you know the constellation Orion. You can go out on, especially on a winter's night, above the horizon, and you see the three bright stars in the belt of Orion, and then up to the upper left, circled here with a yellow dotted line, is the bright orange star, which marks the shoulder of Orion the Hunter. And it has been known for a long time to be a very, very familiar landmark in the sky. As a matter of fact, if you go to the Lascaux caves in the southwestern part of France, you can look at the cave drawings that were made, oh my goodness, 20,000 years ago. And they actually mark out the constellation Orion, Aldebaran, Taurus, the Pleiades, in the amazing figures of the bulls and the cows and all the animals that are running around the walls of the cave. And archaeologists have picked out the constellation Orion. So not only Aborigines in Australia, not only sheep herders in Arab countries, but down in the Lascaux caves, you can see the constellation Orion. And it was about 100 years ago, 101 now years ago, when the first measurement of the diameter of a star, other than the sun, and this is Betelgeuse, was made at the Mount Wilson Observatory using a very clever technique of interferometry by placing mirrors on the beams, on steel beams on either side of a very large telescope. And the New York Times thought it was so important, they put it above the fold on the 30th of December, 100 years ago, 1920, 101 years ago, saying that it was a colossus of the skies. And actually, the measurement that they did then of Betelgeuse was pretty good and consistent with what we see today. Let me just give you a quick summary of what the star is. It's what we call a supergiant star. It's very big. It's much heavier than our sun, maybe 20 times the weight of our sun, and it's also big. It's about 1,000 times, 900 to 1,000 times the size of the sun. And the other interesting point is that it's only 700 light years away. But remember, that means that the light that we're seeing tonight started in 1300 AD. So whatever it did back 700 years ago is what's coming to us now. And it's a cool star. It's now about 3,600 degrees. Our sun is hotter. Our sun is about 5,500 degrees. This is a very big, cool star. And the fact that it's big is just amazing. Compared to all other stars, Betelgeuse is the king, the beast of the jungle, the king of the jungle. Compared to the stars like Antares, stars like Aldebaran, or even our sun, which is marked as Soleil here in, I think this must be a French slide. So the sun is 1,000 times smaller in radius than Betelgeuse. So if we took Betelgeuse and put it where the sun was, in the center of our solar system, it's so big that it would extend out to the radius of Jupiter, the distance of Jupiter from the sun. I mean, that's how big it would be if it would be in the center of our solar system. And of course, completely swallow up, Mars, Earth, Venus, and Mercury. But the fact that it's big also offers a wonderful opportunity, and that is that it is the largest star in apparent diameter, with exception of the sun, obviously, but the largest star outside of the sun where we can actually resolve parts of the surface. Most stars are just points of light, and when we have to study them, we have to study them by looking at all the light from the whole star. But with Betelgeuse, as I'll show you, we've been able to look at different parts of the surface. And that's where it's been very exciting, because we've seen what's going on the surface of a star that's quite different from the sun. And it was actually very surprising when this first happened. Let me remind you a little bit about stellar physics. Stars come in various sizes and various weights and various masses and in various temperatures. And most of the stars fall into what we call sequences or groups. And you see this line of stars starting from Spica up here, the hot, bright blue stars, and then proceeding down through the sun, and then down to the small M dwarfs. This is a plot showing the temperature and the brightness, so that the cool stars are down here in the lower right, the hot stars are on the left side of the diagram, and the brightest ones are at the top left. And where is Betelgeuse? It's way up here. It's a winner in the brightest, coolest column of all the stars. So the current state is that it is a very massive star, and it's also very highly evolved. In other words, it originally started out on what we call the main sequence when it was just born, and it had a mass of about 20 times the solar mass. But then, as you know, stars have nuclear processes ongoing in their core, and they start burning hydrogen, and then when they finish burning hydrogen, they move on to helium, and then they move from helium into carbon and so forth. And we think that Betelgeuse is in one of these in a very evolved state. The core has contracted, and now it's burned its hydrogen, and now it's burning helium and changing that into carbon in the very core of the star. So what does a star like this look like when you're just watching the light and seeing how it's behaving? This star has been observed for a long time. I think the first record of visual estimates, that's just looking out and comparing the brightness of Betelgeuse to other stars, started around 1840. And people realized that it varied. And then as photometers, that's more sophisticated equipment, became available than just the naked eye, they realized that it had a period. And in a matter of fact, it has two periods. It has a period of about 400 days, which is caused by pulsation. And you can see this, we've assembled everything, all the observations from 1894 to around 2019, the beginning of 2019. And you see that there is this short period. This is like a 400-day oscillation in the optical light. That's the total light that we see on the ground, essentially with our eyes. And then there's also a longer period that may be several years, 5 or 6 years long. We think that the 400-day period is a pulsation period, and that's confirmed, as we'll see, by measurements of the radial velocity, the surface of the star, as it moves in and out. So we believe that this 400-day, 420-day period is a pulsation period, and then there's this longer period, which may be a more fundamental characteristic of waves in the star. But the one that concerns us and that we can easily measure is this 400-day period. And you can see it went on for a number, almost over a century, and just behaved in a reasonable way. These are magnitudes, and if you on the scale shows that it varies from about 0.5 to maybe 1 or 1.2, and it's been pretty consistent in that variation. Now, I want to let you look up close and personal at Betelgeuse, and we were able to use the Hubble faint object camera, which had very high spatial resolution, to take an image. This is the first direct image of the surface of a star, other than the sun, and we made this image in the ultraviolet. Now, the surface that you see of a star, or of the sun too, is cool. But then above that surface, there's an extended atmosphere, and this atmosphere is heated, we believe, by pulsation and perhaps by magnetic activity. And so this makes the atmosphere hotter outside, and it makes it bigger than the surface. And in fact, when we measured this with the Hubble Space Telescope, we discovered that the size in the ultraviolet was 3 times larger than the optical size, and we found a hot spot. You can see a very bright yellow spot that we detected on the surface of the star. And it's big. It's maybe a quarter of the size of the disk of the star. And this is totally different from the sun. I mean, the sun has a lot of convective cells, and the cells are perhaps, the new DKIS telescope up in Haleakala has measured the size of the cells, and they're about the size of Texas. But this is 1,000 times that. Very, very big cells, which are formed by, we believe, by convection. Convection happens when there's heat at the bottom of an atmosphere, and this heat tries to get out, and it starts making the atmosphere turn over and roll over as the heat rises out, and these big convective cells appear. We were so curious about that. We wondered how did it change, and did it change? And so we went back a number of years later continuously and took more images of Betelgeuse. And what I'm showing you here are how Betelgeuse varies. Just as a matter of comparison, this image in the upper left-hand corner marked HZ4, that's a white dwarf. So that's what an unresolved image looks like to the Hubble Space Telescope. But the other images here, the other 7 images, are all made in the ultraviolet, made with the Hubble, and they all have the same exposure time, and the sensitivity didn't change. So just looking at them, you can see that the position of this bright spot, this bright pixel, the bright hot convective cells, moves around, becomes larger, becomes dimmer. We didn't have enough observing time to be able to find a period to the appearance, but clearly you can see that there is variation on the surface. So here we have a star with big convective cells, a big star, big convective cells, and these cells come and go. So that's in the back of our mind whenever we think about Betelgeuse. Well, and we've also been able, with many techniques, to image the surface of the star. Now, this is sort of 20 years later since our first Hubble image, and they've used interferometry at various telescopes in the Southern Hemisphere and in the Northern Hemisphere. And they find, for instance, in the left, that in these infrared images, and here we're looking also at the surface, pretty close to the surface, 2 bright spots at this point, and then people are trying to model it. And they're sort of successful. They can model some of the spots, but not all of the spots, but they're making progress in that. And we also see that these spots, again, confirm what we found in the ultraviolet. The ultraviolet, of course, we're observing farther out in the atmosphere, and this is down towards the surface, where they did find a lot of variability of these appearance of the star. And now another amazing thing that we could do with the Hubble, as we noted, Betelgeuse is big, really big, and we have a small aperture. That means a small opening to collect the light from Betelgeuse. And we were able to take this aperture you see in the left. This happened to be an early one where we had a square aperture here, and we moved it slowly across the image of the star. Each little white point marks a place where we obtained a spectrum of the star. And by looking at that spectrum, we could see how the star was rotating. And it appeared to us that the bright spot that we saw was at the pole, because we could determine the rotation, because one limb rotates in one direction and another limb of the star rotates in another direction. And that we could measure by looking at the spectrum, of where we can measure the light that's coming from the molecules and the atoms and the ions in the surface of the star, and it reflects the motion of the star. And just to confirm that, yes, maybe that really is the pole of the star where things are rotating, people have observed plumes of material that have been thrown off by the star. These stars are all very unstable. They're like clouds, very low density, and they're losing material in, well, we're learning how they lose material. Sometimes we think it's a steady stream of a wind. Sometimes we think it's clumps coming out. So we're still tracing that out. And then now we've been using ALMA, which is a wonderful interferometer, radio interferometer in Chile, in the Atacama Desert. And they are able to get very high spatial resolution. You can see the size of their resolution by this little oval white in the corner of the image. And then they can also measure molecules. And at that time, they discovered that the bright spot was in the other side. It was not in the southwest of the star, but it was up here in the northeast of the star. And they say that they found a plume of material that had been ejected from that particular pole of the star at that time. So that there seems to be dust coming away and material floating away from the star at various times and in various directions. Okay. Well, let's find out what happened in 2020 and 2019. And what I'm showing you here is the light curve. This is the optical light, the visual light curve of Betelgeuse from the past 7 years. And you can see it was happily going along showing the minimum every roughly 420 days. There's always a gap, because when we're observing from the Earth moves around the sun, and sometimes when we're looking at the sun is in front of, or the sun is projected against Betelgeuse in that direction. So Betelgeuse sort of goes behind the sun, and we can't see it, and that's why we have these gaps in the light curve. Well, everything was going along fine, and then this was a little bit dimmer, and this was probably in the end of 2018, and then trouble really started in December 2019, when this went down. This is below a magnitude 1. Normally, it varies between, you can see here, 0.1 and maybe 1, but it started really going down, and then reached a minimum, a very deep minimum, historic minimum. Has never been this faint before, of about 1.6, 1.7 optical magnitudes at the beginning of February in 2020. And this, of course, was crazy. I mean, the Twitter sphere went, exploded, social media, newspapers, TV, everyone was getting worried. As a matter of fact, we were at a big astronomical meeting in Honolulu, and we all went out from the hotel and looked up at the sky, and the constellation just looked weird. Betelgeuse should have been there, and it was very, very faint. And if you went on Twitter, someone said, "My calculations say it's going to explode tomorrow," and he put #run. Well, I'm not sure where you run exactly, but this made all the newspapers and the headlines of what was going on with Betelgeuse. Let me remind you what the state of Betelgeuse is and what might happen. We heard earlier how we fuse the nuclear reactions in the core of the star change as they move from one element to another. So once it uses its hydrogen up to helium, then goes from helium to carbon, and each one takes a certain amount of time, but the time gets shorter and shorter and shorter, so that finally, when it has neon and they're fusing that to oxygen, that's maybe a time scale of a year, and then we move to 6 months. But silicon to iron, the theorists tell us it's going to take 1 day, and then boom. So as fusion advances, we think it's going to become more and more unstable. But the interesting thing is that no one really knows what a supergiant looks like right before it explodes. We know that maybe 2 months, a year, 2 years ahead, what it might do and how it might appear. But right yet we don't have the ability or the capability to follow all stars that might become supernovae, night by night by night, waiting for it to happen. And I can tell you now, you can rest easy tonight. It's not going to go off. We've got maybe another 10,000 years, so don't lose any sleep tonight, please. But likely it will explode as a supernova. The estimates vary, but the interesting thing is that when it does blow up as a supernova, it'll maybe as a bright star in the daylight. It'll be as bright as the moon, and cast, as the theorists say, cast strong shadows on the ground. So, and certainly do a job on nighttime astronomy, that's for sure, if you want to look at faint galaxies. Okay, so at the beginning of 2019, a number of us got together and decided that the only way to really understand Betelgeuse was to use all of these capabilities from the ground and from space and try to look at different levels of the atmosphere all the time and see if we can understand what makes the star work, what makes the atmosphere work, how it loses material, when it loses material, why it loses material. And we called ourselves the mob for months of Betelgeuse. And we managed to commandeer lots of equipment from interferometers, from the Hubble Space Telescope, from the large in the center here. You see the very large telescopes that are the telescopes at the European Southern Observatory in Chile. We have radio telescopes, optical telescopes, high-resolution spectrometers, interferometers. This happens to be in part of Lowell Observatory in Arizona, to try to look at Betelgeuse using all of this equipment together so that maybe we could understand and capture what's going on. So let me tell you about a year in the life, this exciting year in the life of Betelgeuse. And I'm going to start in the spring, January to March, roughly, of 2019. And on the left in January, we took a picture with an imager called Sphere at the Southern Observatory in Chile, an optical image. And you can see it looks very similar to what we have seen before. There's a bright convective spot here, and then there's it's fairly spherical, and it looked perfectly fine and normal. But then some really exciting things happened using spectra. And there's a piece of a spectrum on the right. Now, what this does is we have an instrument where we take the light and we break it up into its colors. In this particular spectrum takes all the light from all the stars. It doesn't have it from any particular place. But the gal, Katerina Kravchenko, did something very clever. They developed what we call a tomographic analysis. All of these zigzaggy things, these are all absorption lines produced in the atmosphere of the star, and they can be identified with different elements, whether it's iron or titanium or silicon or oxygen. We know what all these lines are. But even more important is that when we make models of the atmosphere, we discover that some lines are formed deep down and other lines are formed farther up in the atmosphere. So, for instance, we might say those lines, red lines, are formed deep down in the atmosphere, and then the blue lines are formed in our model, we can tell, are formed farther out in the atmosphere. Well, now if we separate out all the lines and watch how they behave, we can infer what the motions are and what's going on in the atmosphere at different levels of the atmosphere. And when she did that in the spring of 2019, she discovered that the surface was beginning to expand. Now, the optical light looked perfectly fine. Nothing strange had happened, but she could tell that the dynamics of the atmosphere had started to change and the surface had started to expand. And this was when the optical light, as I said, was perfectly fine and everyone was happily watching the Orion constellation. It looked perfectly normal. And then we have other folks who are measuring the radial velocity. That's the motion of the star as it moves in and out. The surface moves in and out. And they've been doing this for a number of years. And you can see it follows a 400-day period, which is roughly, that's the blue circles here. The blue dots are the radial velocity. That's how fast the star is moving towards us or away from us. And what we discovered was that during September and November, now this is 6 months later, at this time it had reached a maximum outflow. Now these observations were made, nowadays astronomy is doing amazing things. These were made with a totally automated telescope on the island of Tenerife near the T80 volcano. And so every night this telescope automatically would point to Betelgeuse and take a spectrum and then reduce it and measure the motion of the atmosphere of Betelgeuse. And we discovered that during January, it had started moving out. It's coming towards us as it moves down and moves towards the lower velocities in this case. Well, so we went back one. And we discovered that in September through November, it was at a very maximum outflow. And it was just about this time that we had the Hubble Space Telescope. And again, with Hubble, this time we were able to use a very small aperture. And you see in the right image, this little white rectangle that marks the size of the slit, the aperture that we use with the STIS instrument, a spectroscope on the Hubble Space Telescope. And what we were able to do is move this slit and take a spectrum at any one of 7 or 8 positions as we moved in the direction of the arrow across the image of the star. And then we could look at the energy coming out in various lines. And the thing that was amazing, these are lines in the chromosphere, so they're strong emission lines above the surface. And what I'm showing you here is a picture of the strength of the lines as we moved across the disk. Now, the center of the star is here, And when we start from the right, which is in the northwest, and move across, you see the change. And this happened, these open little figures, symbols, this is what happened in January through March. I mean, everything looked fine and wonderful, peaceful. And then all of a sudden, when we went back in September, we saw these red symbols here. September, October, and November, we saw this enormous increase in the emission, the strength of the radiation from magnesium-2, mainly in the southern hemisphere of the star. And so what it's telling us is that there was a cloud of magnesium-2 suddenly appeared in those 3 months from the southern hemisphere of the star. Now, there's something else we could also do. Spectroscopy is very powerful, and we can look at certain emission lines, and by looking at the strength of these lines, we can tell what the density is in that particular atom, in that particular cloud. And what we found by looking at these are lines of carbon-2, we look at the strength of this line relative to this line, and what we found out was that in September and December, in the southern part of the star, where these little red symbols are, that's where there was a higher density. So suddenly, January, March, things were fine. And then suddenly in September through December, when we were observing, it could have happened before too. We obviously don't have any information about that. But suddenly, the density, this was not only a bigger cloud, but a very dense cloud, much denser than the cloud, than the atmosphere had been before, was appearing in the southern part of the star. And then it went back to sort of normal values again. So we now see that there's something going from the south. It's dense, and we then can even do more by looking at the shapes of the lines. And you see the lines are similar to this cartoon on the left, which are some calculations. And what it's telling us is that material is moving out very fast, because we see this enhancement of the outward moving side of the line. And that happened right in September, October, December. Or November, actually the end of November, when the ratio changed enormously from what it had been in the spring, and then what happened in February and April. So clearly there was a pulse of material, high density, that was shot out from the southern hemisphere of the star during that time. Okay, now our Hubble visits coincided with the decrease, and then finally the minimum, and also the maximum outflow velocity. So what we suspect from that is that this time, because it coincided with the outward radial motion of the pulsation cycle, that we probably had a bright convective cell on the surface of the star, and a motion combined with the pulsation to eject material. And we suspect that it started from January to March 2019, when the surface showed this expanding material. And now it is progressing through the upper layers of the atmosphere. And we saw it with Hubble in the chromosphere. Remember that even if you're going 5 kilometers a second, which is by an astronomer's calculation, that's not very fast, but 5 kilometers a second, it would take 6 months to reach the magnesium-2 lines. And that's about the time from March to September when we saw it. And 5 kilometers a second, as I said, doesn't sound very fast to astronomers, but you know, that's 10,000 miles an hour. So it's really, really fast. It's really fast. And it takes about 160 days to get out to where the magnesium-2 lines were formed. So then we continued with stereo and imaged the star in December, late December. Now, this is after we saw something pass through the chromosphere. We saw this ejected material. And we took another image in December, and look, compare it to the January image, and you can see the bottom half of the star is dark. I mean, like, it's dark. What happened? And then we continued through January and March, and you can see this dark shadow on the southern part of the star. Well, we think this is what happened. that in September, October, November, driven by the surface activity on the star, that the star ejected a lot of hot, dense material, which then traveled out through the atmosphere. And as it went out, it gets cooler. The surface is cool, and then the chromosphere is warmer, and then we believe the atmosphere is cooler further out. And further out, as it gets cooler, molecules will form, and then we think dust will form. And some polarization has been measured, which is an indicator that there may be dust in the outer atmosphere. We think the dust formation is the most likely model. But, you know, there are a lot of other questions. People have continued to measure it, and we don't know what the effect of losing all this material is on the surface of the star. I mean, was it suddenly less dense? Was it suddenly cooler? Did molecules form first? And maybe the molecules had some dimming effect on the optical part of the star. Will the star show lasting effects of this event? In other words, will it come back again? We've never seen this before. Is it likely to repeat? Will it keep on going? We really don't know. And it did do something rather unusual right afterwards. It didn't go back to its 400-day cycle that we know and love and recognize. It didn't happen. But then we were able to do something else, which is kind of fun. As I mentioned, there are always gaps in the light curves because, as you see here, from about May to August, May to August, the sun blocks our access to Betelgeuse. And I realized that there are satellites that we have, solar satellites, that are in the Earth orbit, but they follow the Earth by about 3 or 4 months in Earth orbit, and they have cameras on them. Well, if they follow the Earth, this means that when the Earth is in July and we cannot see Betelgeuse, it's perfectly fine for stereo to see it because stereo only thinks it's March or April, and it can see it. So I called up the folks on working stereo and said, say, can you guys slew your spacecraft over and take pictures of the sky? And we could see how bright Betelgeuse is. And they did. And we're still doing it. And we were able to fill in, and we still have filled in with stereo what's been happening during these gaps when we can't see it from the surface of the Earth. Another amazing thing which has just appeared, and that is that there are many meteorological satellites. There's one in particular called Himawari, which is a Japanese satellite. And these meteorological satellites take images of the Earth in various filters because they're watching storms and hurricanes and all the good things that meteorologists love to watch. But in the corner of the images, they can access the black night sky. And since Betelgeuse is close to the ecliptic, close to the path of the sun and the Earth, we can pick up Betelgeuse. And so this graduate student at Tokyo found Betelgeuse in these Japanese satellite images, and you see it there, and then you see it here. And they can actually now measure it all the time. And I just heard this afternoon that we're doing it too with the GOES satellites, GOES, a wonderful observer from the AAVSO, Tom Calderwood, has managed to get all the GOES images, and now he's finding Betelgeuse in those. So we're going to have lots more data of Betelgeuse and what's happening. So what's happening right now? Well, you know, it missed its pulsation. You see here's the Great Dimming, okay? And I've overlaid it with a curve showing 420 days. And you see that, sure enough, in January 2019, it was fine. And January 2020, there was another minimum, a real minimum. But then wait a minute, there should have been another one this January, and nothing has happened. It's sort of bobbing along. The red points are the stereo points from last year. We got some from this year. And then I just put last night's observation. Actually, there's a very imaginative amateur astronomer in Germany who's figured out how to take daytime images of the star, Betelgeuse, in the daytime. And he seems to be getting pretty good results. So I put his last night image, last night value, or yesterday's value on the top. So maybe it's topping out. Maybe it's going back to its 420-day period, but I don't know. Will it resume or not? Stay tuned. We shall see. So look at the star tonight or when it comes back and pretty soon in September. Enjoy it while we can. Thank you.
Thank you, Andrea, for that fascinating presentation. I really enjoyed it. So everyone who's watching.
Come back to you.
Oh, sure.
Yeah, I think I'm going to come back to you, I think. Let me see. There we go. Okay.
No, thank you again, Andrea. So everyone who's watching on YouTube or Facebook, it's now time for the Q&A portion of our lecture. So if you can just start commenting on Facebook or YouTube, if you have any questions for Andrea, that would be great. And Andrea, to kick us off, I want to ask you something that I thought of while you were presenting. So are there planets around Betelgeuse like there are planets around the sun? And if so, how would they be affected by a dimming?
Ooh, well, we don't think there are planets around Betelgeuse. Actually, we think Betelgeuse has a very torrid history. It's rotating very quickly, and too quickly, we think. And one of the theories is that it had a companion, and it managed to swallow the companion as it expanded. And it probably would have swallowed planets too. So I'm sorry, Nadia.
Okay.
Well, you know, our sun is going to become a red giant. I mean, we don't lose sleep over that either, but not good for planets. But right. They are finding planets. I mean, obviously studying exoplanets is a very exciting field right now. And planets have been found around practically every kind of star, even white dwarfs, stars that have gone through their evolution and become giants. And there still seem to be remnant planets around them. So we're all looking and studying, and lots of good satellites up there, and lots of good ground-based observations. And but we think that, as we said, that there was a strange history of Betelgeuse, that it may have been a binary, because when we first found the rotation, everyone said, big mistake. And we said, oh, well, maybe it swallowed a planet, sort of being facetious about it. Yeah. But people have now done more calculus. Planets won't give it enough angular momentum to speed it up like that. But another star would. And frequently these early B stars, these very massive stars, are formed in binary systems. And so we suspect that it had a companion at one point, which is no longer there, and we no longer see it.
Wow.
Oh, yeah. There's a big history behind it.
Okay. Well, while we were talking, some more questions came in. So let me pull one up. Okay, from Jeremiah on YouTube. Does this change our position on when the star may finally go supernova?
Not really. But let's keep looking at it. As a matter of fact, as I mentioned, I think once the Rubin telescope is in operation in Chile, they are going to start taking many photographs of the sky every night. So we can start looking at stars. We don't know what a star does right before it goes supernova. I might tell you a year before, or 2 years, or 5 years, but nothing like hide under the desk because it's going to happen tonight, you see. So no, it doesn't really change our estimate of when it goes supernova. That's what I'm saying now. But, you know, astronomy, that's why astronomy is exciting. You know, go out and look tonight and see.
Okay, thank you for your question, Jeremiah. Let me go ahead and pick another one. Okay, from SpiceX 4K. How will the James Webb Space Telescope aid in studying Betelgeuse?
James Webb is an infrared telescope. and it makes infrared spectra. And the infrared spectrum is unexplored and very rich in determining temperatures, molecular structure, a molecule abundance, and will tell us a lot about the circumstellar environment of Betelgeuse. In other words, it will tell us how dust develops. It will also, hopefully, combined with the Hubble results, we can see. The one surprising thing is that it looks like the star is not only losing material from the poles where you might expect it's easy to come up, but this time it appeared to come from a different part of the star. And this is the only star where we can really look at it and see where the material is being ejected. People have looked at another very bright star called VY Canis Majoris, where they cannot see the star because it's enshrouded in dust and things, but they can see material that's been shot out from the star, and they find that it's shot out all over. There's not a preferential direction, which tells us that what we're seeing in Betelgeuse is probably not that unusual. I mean, that maybe at the beginning we only saw things emitted from the poles, but this other star is telling us that it can come from anywhere. So it's enlarging our horizons about how stars are losing material, and it's also can be in explosive events. I mean, that's something else. I mean, when we think about our sun, we think about, which we know very well, which we think about the wind is moving out sort of like a gentle, every now and then it's faster and slower and things like that. But it's a pretty steady wind. And what we're seeing in this star and other supergiants is that it may be bursty, and we may get these special events where material is shot out. I mean, this was about a tenth of the solar total yearly mass loss from the sun that went out, from the star that went out in this period of 2 months or 3 months. Yeah.
Okay. All right. Thank you for your question, SpiceX. All right. So from Christina on YouTube, is there other citizen science being used to look through the data?
That's good. That's a good question. Citizen science is being used a lot to search for exoplanets from tests from Kepler, other space missions. We don't, as far as I know, we don't have a citizen science group to work on this. We may need it now that we have all the meteorological satellites and lots of data coming in. But you know what we do have that I should mention is the American Association of Variable Star Observers, the AAVSO. And they are amateurs, citizen science, but they are amateurs who frequently have their own equipment, their own observatories, and they make observations and put them onto an open public database. And that's where I go. That's where I went this afternoon to find out what the latest measures were yesterday of Betelgeuse. It's aavso.org, and that they have a lot of resources there with a lot of light curves, a lot of data, and a lot of amateurs. I mean, hundreds of amateurs around the world that contribute to this. So that's the biggest citizen science that I know of, but we don't have a group similar to that looking for exoplanets yet. But that's a good idea.
All right. Thank you, Christina. Next question from John Lewis on YouTube. Awesome talk, Andrea. Are there any thoughts on what caused Betelgeuse to eject a dust cloud and how often that might occur in a direction we can't see?
Well, this is the first big dust cloud explosion we've seen, so it's hard to say what's going to happen again. But what's interesting is, you know, it happened at the same time as the pulsation was moving out. So so I think the two things, like a convective cell and the pulsation, both helped to get this thing going. And you're right, we're only looking at one part of the star, and something could be happening on the other part. We know that Betelgeuse has been losing material because if you look at, there are some infrared images from Herschel, which is a European Space Agency satellite, showing rings of circumstellar material that's happened in the past, and a bow shock, because by the way, Betelgeuse is also moving very quickly, anomalously quickly, as if it was ejected from the Orion Nebula at some point. Maybe when it had its binary event, I'm not quite sure. But we don't know how often it does occur. That's why we're trying to watch it. And you are right that it undoubtedly there was one on the other side, or there could be one on the other side that we just don't know. We do know it's losing mass all the time. I mean, we know that it's a very high mass loss rate, sort of a factor of I'm trying to think, 10 million times faster, 10 million times more material than the sun. So that's happening, and that's happening all the time. And now with the spatial resolution, we're able to see where it's coming from. Most of the mass loss rate estimates are made by looking at the star as a point source, so we don't know where it's coming from. But it's certainly could come from the back as well. I agree. And that's why we were looking at this other star, this VY Canis Majoris, which was being done by a gal, Roberta Humphreys in Minnesota, where she looks all around it and she can see knots of material that have been thrown out from this star in different directions. So it does look like there's not a special place where it's losing material. It's losing it everywhere. So I would expect our friend Betelgeuse is doing the same thing.
All right. Thank you, John. Next question from John on Facebook. Have any other less well-known supergiants exhibited such a dimming?
Not the very coolest ones like this, but there are some stars which are yellow supergiants. So that means they're hotter. And they're called our corona borealis variables. And what they see in these stars, now these are about the same mass as Betelgeuse, but they're in a different stage of evolution. They're warmer. They're moving perhaps to the right across that diagram that I showed you. And what they do is they eject material very quickly, 400, 500 kilometers a second. And that material turns to carbon dust like that. I mean, within 2 days, it drops 10 magnitudes or 9 magnitudes. I mean, really, really drops, okay? So Betelgeuse, by comparison, it only went down a magnitude. But these are yellow hypergiants or yellow supergiants. And they do it much better and much more frequently at that particular stage. Yeah. Okay.
Thanks for your question, John. Next question from an unknown YouTube user. How close would the Earth have to be for a Betelgeuse supernova to cause us trouble?
Someone said to me once that even if it went supernova, there'd only be one extra batch of cosmic rays causing one more cancer death in the United States or something like that. Say the real trouble, well, it's so far away that it's not going to cause us trouble. It'll cause trouble for the nighttime astronomers who want to look at faint galaxies because there'll be this very bright star in the sky, and we'll see it in the daytime, so it would be fun to watch and see what's going on. But don't lose sleep. We're okay.
Good to know. Good to know. Okay, next question from SpiceX again, 4K. How can we be certain that Betelgeuse has no exoplanets if they are in a relatively inclined orbit that does not eclipse Betelgeuse?
Well, people have looked at the radial velocity very carefully. I mean, one of the ways the way that we first discovered an exoplanet back in 1995, when Michel Mayor and Didier Queloz found the 51 Peg, they measured the radial velocity, and when a star and a planet rotate, or the planet rotates around the star, there's a movement of the center of mass, and so that you can see the reflex motion in the star. In other words, it reflects the orbit of the planet, and that's how we first discovered exoplanets. Okay, people have looked carefully at Betelgeuse. At one point, they thought, using a technique called speckle imaging, they thought they found a companion, but that had never been confirmed. Other people have looked and haven't seen it. Admittedly, Betelgeuse has a rather challenging radial velocity curve because sometimes it doesn't behave the way we think it should behave. But to my knowledge, people, well, maybe that's a good thing to do. Maybe people should really look more carefully. They have looked, as I understand. But I don't know if they've really, beaten it into the bushes and down to the ground to look for one. It would have to be very, very far out. Otherwise, it's been gone, long gone, as Betelgeuse evolved and expanded. I mean, if Betelgeuse were in the center of our solar system, it would have swallowed us and Mercury, Venus, Earth, and all the way out to Jupiter. so it would have to be very, very far out to see, and that means also a very, very long period. And those are hard to measure. But maybe people should beat on the light curve a little bit, or the radial velocity curve a little bit more, and see.
Okay, thank you for that, SpiceX. All right, from Simon on YouTube, would a microsat dedicated to observing only Betelgeuse year-round be helpful?
Oh, I think it would be wonderful, but the chances of getting that are tight. Actually, the Japanese meteorological satellite, the guy tells me, he sent me a paper just a few days ago. He thinks they can watch it all the time, and they have calibrated cameras and filters on that satellite, and we have our GOES satellite, and we have archives of GOES satellites, and so of the images that we can all download. So we're now starting to look at that, because we may be able to effectively, thanks to the weatherman, get images of Betelgeuse all the time. And watch it. We also are going back through the Harvard plates. Harvard Observatory used to have a station in Arequipa, Peru, and where they took images of the sky. And there they took images of the Large Magellanic Cloud, which in 1987 hosted one of the most nearby supernovae that we've ever seen. And we've been looking back at those plates. They've all been digitized, and we're in the process of looking, because we believe we have measurements of the brightness of that star right before it exploded, because right now we don't know what happens right before it explodes. So we're pursuing that. But we may be doing it with these weather satellites, which is the kind of a fun use of, an interesting and challenging use of the weather satellites, a peripheral goal.
Okay, something for the future. All right, from Philip on YouTube, how would Betelgeuse's post-nova characteristics compare to the star explosion that gave us the Crab Nebula? That blast happened around 1000 AD, did it not?
You might see something just like that. What can I say? Yeah, people haven't calculated what it would look like afterwards. I think they estimated how bright it's going to be, but how it's going to look afterwards, to appear afterwards. Actually, what's interesting is that how it appears and how the light decays and how the spectrum changes depends on the material that it lost before. So you can watch sort of the history, and that's what we did with the one in the Large Magellanic Cloud. You can watch the early history of losing material as the shock expands into the medium around the circumstellar medium around the star. So we shall see. Yeah.
Okay, thank you, Philip. And let me see. I think that's all. Oh, one more question from Ellen on Facebook. What is the distinction between the star and its atmosphere? Isn't the star a mass of molecules, nothing solid?
Yeah, a star is a gaseous mass. Yes, it's very hot and very dense at the core, and then it becomes cooler as you move away from the core. It becomes less dense, but then magnetic fields heat up the very outer atmosphere, which is what we call the chromosphere. So what you see in the surface is cooler than what is generally further out from the star due to this heating effect of magnetic fields. But yes, the star is not a mass of molecules, are only form where it's cool. The star is a mass of atoms and ions different isotopes of these atoms and different ions. So that means that, like, you take a carbon atom, and it could be neutral and has all of its electrons, but then it loses its electrons as the temperature increases, because the collisions knock the electrons away, so that you can get carbon in various states: carbon 1, carbon 2, carbon 3, carbon 4, etc. And the same with everything else. And you know that all the elements that are in us were made in the stars. I mean, our iron, our silicon, our calcium in our bones, all of this was made of stars. We're made of star stuff. Okay, everything other than the hydrogen, which started, and the deuterium, which started us out, and helium, but all the elements that we know and love are all made in stars. So there's just a cycle of element production and destruction via the stars. If we didn't have the stars, there wouldn't be much here.
Okay, thanks for your question, Ellen. It's almost time to end, but I have one last question just from myself. So is it possible that our sun could dim? And if so, what do you think would happen with the planets around the sun?
Well, the evolution of the sun is such that it's right now it's on what we call the main sequence, and it's going to get brighter. It's not going to dim. I mean, there may be a what we call a Maunder minimum, when there's perhaps no sunspots, but the nuclear processes are going on. They're going on inside, and it's going to get brighter. It's going to become a red giant. It's going to get brighter, and it's going to get cooler. It will never be a supergiant like Betelgeuse, but it will be a giant like Aldebaran, or the giant stars that we see in Gemini or Capella or things like that. Okay, and it will expand. So that's not good news for us on Earth. But as I said, I'm not going to worry, and you don't have to worry either. So.
Wow. Okay. Well, I'm going to close this out then. It's just about 8 p.m. Eastern Time. So thank you again, Andrea. This concludes tonight's New Vistas in Astronomy lecture. Thank you again to everyone who joined us, and especially to everyone who asked questions. I'm so happy you were all so engaged. If you enjoyed this evening's presentation, I want to encourage you to support the Center for Astrophysics and consider giving at the link that's going to appear on your screens now. It's also going to appear in our comments section. Any amount will help support the important research and engineering that happens at the Center for Astrophysics every day in an effort to answer humanity's greatest unresolved questions about the nature of the universe. We look forward to seeing you again next month for our New Vistas in Astronomy lecture on September 30th. It'll be the final presentation of the year for the Fred Lawrence Whipple Observatory. Pioneering astronomer Shep Dolman, the founding director of the Event Horizon Telescope, will be sharing details of how astronomers captured the first image of a black hole in April 2019. Visit our website, cfa.harvard.edu, for more information. Thank you, everyone, and good night.